G'day everyone, I hope everyone's doing pretty well today. So we're going to carry on with our engine build today. Again, don't mind the mess, preferably. We don't have the workshop anymore, so we're just going to improvise. We're going to cover pistons today, so I'm not going to bore you guys with too much details for the guys. I just want to get to the details, so we're just going to jump right into that, about choosing pistons for your build. Okay, so we have two pistons here. This is the old one. This is a JE something. Part number is over there. If you guys can see that. There it's a PN 296904 9277786. This is the ones that were in the engine when I got it. Obviously they didn't make it. I did a whole video on the failure analysis. Long story short, the clearances were not sufficient, and we had all this damage which caused validity in our bores. I'm not going to go too much into that. So we have now gone with replacing them with new ones. So I've got here, the piston I went with this build is the Manly 614005C piston for this. This is a 2618 piston. So reason for this is we are looking at making more of a power build with this one. We're not really too worried about RPM at this stage. And we're looking for strength, reliability, which is why we chose this one. The actual pistons that I wanted for this was the Seiko ones. Unfortunately, I couldn't get them, and these were the ones that were available, so I was like, yeah, right, I'll go with them. They're pretty good. Normally with the EVA builds, or the EVA 10 builds, your go-to is the Seikos with the Manly turbo tough rods. If you scout around the forums, though, most people will say, but it really depends on, like everyone's personal preference. And we're going to dive into these two a little bit here. So long story short, you get two types of pistons. The factory ones, which is, I think it's the Hybiotectic ones, which is a 4032 metal. I only found one set of those available from Vossner, I think, in the UK. They're the only ones that sell them. So Google those if you want those. So they're close to the factory specs. And then you have the other one, which is a 2618, which is this one that I've got here. Much higher, well, not much higher, doesn't have the silicone content. We'll get into that in a second. But you will have a lot of thermal expansion on this, which is something you need to take into account when you're building your engine. Same one as the ones that are in here. Also, we'll get into how that happened a bit later. But for applications, if you're going to be building up to, I would say about power figures about 500, you probably can get away with a 4032. Reason being, it's not going to be that heavy of, well, with modern standards, it's not that heavy of a performance application, and you kind of want to get that rigidity. So the reason why I recommend the 4032 on that is because with your 2618 pistons, you have a lower silicone content. So basically it's a metal, they have silicone, they add on it, they different properties and all that. The factory pistons from Mitsubishi, they're also 4032s. And like I said, Boston's the ones close to them. So they allow, because they've got more silicone, your thermal expansion as things heat up and cool off, your thermal expansion is different. So for example, if I can show you this here, these are the old pistons are in there, and this gudging pin is just in there because it's a relatively cold day. The metal, and this is kind of holding onto that pin, where if it was a bit warmer, I could freely turn this one as it should be. Now, it should actually be allowed to turn, but you've got the breeze there, but that's a topic for another conversation. Yeah, so with the 4032, we've got the higher silicon content, which allows for much tighter tolerances. Now, initially when I first measured up this engine, I was like, oh, we got a little bit of damage on the bore here. I just try to hone it out to like a little bit, tiny little bit bigger. And then I would be able to run the 4032s, but the 4032s were so hard to get that, like I said, only Vossner in the UK had them, and obviously getting them all the way to Australia is going to be a bit of a challenge. So we didn't go that route. And then SSM Performance hooked me up with these guys. Very happy with the quality of these ones. We're going to dive into them now to show you the difference between the, even though they're the same metal and they have the same design. Oh, that's actually the wrong way around. There are differences, as you can see, in difference of your valve clearances here, like small things that you want to look into. And for the average build, if you're just like building something basic, you probably don't have to worry about that. But if you're going for a high performance build, you probably want to look at something like this. Obviously, we're going to push the envelope as much as we can, so we're probably going to end up breaking this engine eventually. But yeah, it's something, you know, I've always wanted to do and document it for you guys to learn. for the community and to improve. So if you have any comments or tips and tricks that you've learned over the years, please drop them in the comments so people can learn. Like I said, this is for learning purposes, educational purposes, and all those other lovely things, right? So 2618, why did I choose the 2618 over the 4032? So with the 4032, with the silicone content being a bit more tight, less thermal expansion, your ductility is lower. So what is ductility? Ductility just means, do I have anything here that's elastic? I'll use this for like a comparison. So with ductility, a metal, I'm using a spring now because the spring is going to flex, but basically they've got a little bit of flex in them, and where if you have a more rigid material, your flex will be less. Now this is a spring, so obviously it's going to flex, but just to drive the point home, I could use the feeler gauge. Yeah, that'll work nicely. That'll be a good demonstration. So yeah, so with the ductility, basically it means if the engine were to knock or anything like that, don't drop the feeler gauge, maybe, not recommended. So yeah, so basically if you were to look at the feeler gauges here, ductility basically allows for flex. So the thinner leaves would take these two for example. I've got the gloves on now, so they're able to flex a bit easier. So it's basically it's elastic, but it's going to bounce back. So that's just ductility. Where a thicker one, it's a bit more rigid. It still has some of that, but it's not as obvious. Basically, it allows the metal to flex and bend back without permanent deformation, which means it loses its shape. That's why some of the pistons go around. They basically deform from that. So aluminium does have a very low yield. Yield is basically when it starts coming apart and bending and breaking and that, compared to steel. But due to its lightweight, not lightweight, I've got to be correct, due to its lower density to volume, its weight is less. So that's perfect application we want for automotive. And honestly, if you put the 2016 next to 4032, they're going to look exactly the same, so you won't really be able to tell the difference. But we went with this one because we have the ductility. As a compromise, we have to give higher cylinder piston to wall clearance. Yeah, that's a great word. So higher piston to wall clearance with this, which allows us to basically, as the engine heats up, that can expand. You can actually calculate that with, I think it's the coefficient of, it's not latent heat of vaporization. What was the word again? But basically, you have a coefficient of thermal expansion. I think that's what it's called, which basically is your material, your ratio, and your diameter. So basically, each one of these properties will have that, and you can actually calculate what your final bore is going to be. Now, keeping in mind with your pistons, you have the measuring point. So this is actually tapered. It's actually tapered like this. Get in frame there, so taper like that. So your bore will actually be measured somewhere around about there. They've got a whole thing about that. Now, the mistake that happened with this is that when this engine was previously assembled by the previous owner, and that they didn't pay any attention to these thermal expansions. That's how this happened, because the piston expanded from the heat, because you have a 2618 now in place of a 4032. So you need greater piston to wall clearances. And then as that expanded, this basically started eating away at the cylinder wall. You can actually see that. I wonder how close I can get to that without it losing focus. And you can like see there, it's basically, this presses up against the wall of the cylinder, and you can kind of see that taper, how it kind of like tapers down at the top. And then you start like rubbing against the cylinder. I mean, you can even hear the difference there, from there to here. It's just so much more louder. But yeah, so that's the thing, because it didn't account for the increase in thermal expansion. So how do we fix that? We basically took the block, we rebored it. It was already out of round, so we upsized it anyway. But normally if you want to go factory, you want to upsize it. So if I were to basically, let's say the bores went out of round, I could have just taken these ones that have been all damaged there, given it a light hoe, and drop in 4032s, I'm happy to go. So that was the original plan. It didn't work out, so we have to go full rebuild on this. And I would like to kind of show you the comparison now between the weights. Is that a 0 there? There we go. Seems pretty good. Okay, so I want to see if you guys can see that, those figures on that scale. Bugs flying around here. Let's see. Let me see if I can set this up better quickly. Okay, that is a bit of a precarious position, but I think we got the angle right there. So let's look at what we're going to do here. So we're just going to measure this. Obviously, we're going to make sure there's no debris on this. Give it a little bit of rag, wipe it off, make sure we've got no debris there. I probably want to do this on a desk. I don't have a desk because no workshop anymore, but anyway, we'll be able to make the plan flat surface just as good. So we're going to zero that, and let's just measure this one. So this is pretty much fresh out the box. We're going to measure this one here. It comes in at 335 grams, and then comparing it to the old ones here, this is the JE, I think it's a JE's 317. So this is where the small differences come in, where you have to kind of like decide what you want to do. Do you want to go for a high RPM build? Because the heavier you make the piston, the more work the engine has to do to get the piston up and then pull it back down. And it's the more weight you have, slower your RPM response, more weight. But obviously if you have a lot of boost, you need that strength. So basically, the more mass you have, normally the stronger your piston is. The less mass you have, I wouldn't say it's weaker, but obviously if you don't have as much support, it's not going to last as long. And obviously with the balancing, it's a whole thing. So if we were to just look at our new set, so let's measure these ones out here, the new set. So this one's 535, and let's get the other ones out the box here. So these are the new ones. 353, and then this one over here, 354. So even though they do at the factory, they do work hard to get these things as close as you can, you're not going to get them perfect. So 354, I just want to measure these again because that was different readings from what I got before. 354, 353, 353, it should be 354, come on, 353, okay, so that differs. So what are we going to do with the weights now, because the weights are obviously different. So if you're just running with normal applications, like I said, sub 500, probably don't have to worry about this. I'm a little bit of a perfectionist. it kind of annoys me when it's there, so I want them to be perfect. So what can we do? We can basically balance these with the gudging pins. So if we take these gudging pins over here, or wrist pins, or whatever they call them, depending on where around the world. And again, obviously wearing our nitrile gloves, so we don't, because the oils and things on your hand will make these things corrode, so you don't want to do that. So let's measure these out. 117, 115, 114, 115. So you probably want to measure these a few times. So you can actually match these weights with the pistons to get your similar weights together. So 116, I think this was the 113, I think it was 554, right? So you want to weigh them about 3 times so you get a good average. 353, because nothing is real perfect these days. 353. So if we put that one in, we'll go up to 471. Let's have a look at this one. 353, 468. Let's see if I can get another one there. 468. So let's see if I can play around with this a bit, get a bit closer. 470. So let's go with 470 on that one. Try and get them all to 470. That's 470 right there. And this guy here, 470. And then if I have done this correctly, hopefully, come on, 470. Here we go. It's a bit lighter. Let's just measure that a few times. Well, let's zero the scale again, because you always got to work with the weight of your lightest piston. And yes, there's a bit also. Obviously, like with this being lighter, we're going to try and make this one heavier because we want to get that 470 there. Either we have to take everything down to 469. So let me quickly mess around with 469. There we go. We've got 469 over there. We had 470, so this is too heavy, that's too light, so we'll swap these two gudging pins and then give that a check again. So 469, 470, so this one's a bit heavier now, and then that should be 469. Come on, 469. There we go, right. So now instead of having to downset the weight of 3 different pistons, we just have to basically take this one and drop it down to, she's still a little bit, let's get this thing properly weighed. percent. So we're a gram over, so we can take that off with a little bit of effort. Now there's still another trick we can do. We can still use our wrist pins. Wrist pins, what am I saying? Circlips. So they come into a total of 7 grams, so we'll probably get a bit of weight there. And then obviously our piston rings, we still got a few grams there we can play around with, so that's something we can take into account on that, which is basically how we're going to go around balancing things. So that covers the basic of the pistons, the metals to use, and obviously the weight of that, which we want to take into account. So let's compare these to the old ones. Here we have with the wrist pin on the ring. I can't do with the wrist pin on the rings because the other one's empty. This is the bare one. So let's compare this one here with its wrist pin, which was over there. So that's about 423 grams to this side compared to 468. So 468 versus 420. So there's about 80 grams. Is my math correct? 460. Yes, 40 grams. So 40 is 160 grams of weight more added on here. And that just gives you the idea of, like, you know, what we're working with here. So interesting thing here, if you look at this one here, we spent 101 grams. This one here comes in 115, and you can just see that cross-sectional area, hold it there. So cross-sectional area here is a lot bigger than that one. So this pin is going to be a lot stronger. And mind you, these things cost very similar in pricing. So it really does depend. If you want to have high revs, run like an H-beam setup and a nicely aspirated engine, you probably want to go with these JE pistons. If you want to go with for strength and reliability, you probably want to go something a bit higher. Yeah, these ones are still a little bit cold. Because the damn flipping snap ring is in there. Yeah, righto. So yeah, slightly getting there. So as you can see, it's a bit tight. Now, interesting thing, if you have your assemblies that you're running and suddenly your wrist pins can't slide in and out, it does point to deformation on this, which means that's one sign you can look at to determine if you are getting any deformation, like the piston's basically losing its shape and that. So that's basically the section of there. So I'm not going to bore you guys with too many details, but that's basically what it comes down to. We've just done pistons on this. We haven't even done the rods yet, so I'll probably make that in a second video. So let's look at our bores and how we're basically going to do this. So let's let me get that set up. Okay, so here we have our little setup. Camera's kind of hanging by face, so just bear with me, guys. I just want to point out one thing that I also noticed between this here. Just going to drop back on the scale. If you guys can see the figures there. Yeah, you can see the figures here. That's close enough. I'm going to zero that. And then looking with the old scales. Oh, the old scale. What am I saying? With the old piston setups with the gauging pins. 446 on that one. That one there. 446. I think this one here was completely over like 440. 445. So, and if you look at the areas where you were to like remove mass on the pistons, no effort was made to balance these pistons at all. No effort was made. There are no marks on the gauging pins. None of them have been balanced. So they just basically took these, slap them on, sent it, which is fine if you're doing like a Honda or something and you want to get VTEC to kick in and everything, but not when you're building an Evo. That's just not. See, that's 105. The other pin was 101. They really are not the same. Like, there was a lot of place here, and they just didn't run it accordingly. Not trying to. I don't know who the guy was that built it, but it's just those little things that basically get your engine to run better than the other guy. Okay, so now we have a bit of a rainstorm coming in. Might have to redo this video. Still thinking about it. But yeah. So next thing we got to do is we got to check that our bore clearances are correct. So as our pistons will basically heat up and expand, so these things will basically heat up, and then it's never going to look this nice again once you have it in the engine. So, you know, enjoy the pretty parts while they're all there. They're not going to look like that again. So as our piston will, I'm not going to drop it in because there's put nothing at the bottom, but as our piston will go in, like you could see, we have a lot of play there. That's your thermal expansion that's going to affect it there, and we need to check that our piston rings are going to seal properly. So very nice of Manny to supply us with this information. But if you get your proper OEM things, you get a Le Papier from Piriki. And we're basically looking at our specs here. So it gives you all the details you need of the pistons and that, all your oil ring rail supports, your sports compact pistons, and everything you need to know is there. Pretty good information. So interesting here to look at is basically fuels you're trying to run. So you have your high risk applications, nitro, street, all that other stuff. I don't want to put nitros on my car, so we're not going to be looking at that. But you have your fuel, gas, alky, E85, and then you have your bore times ring gap. Now this is in inches, so it's a good idea to get used to working in inches. And then when you are, so we had to rebore this block, right? So we basically factored in our ring gap. So here even have a little chart there that says, you know, all ring gaps and top ring compression. I disagree with this. Reason being is that is on a working surface. So you've got your wrist pin, which is going to run wrist pin on that. So exhaust is that side. So yeah, so your wrist pin's going to run like that, and your top ring gap is going to be there. Now I disagree with that. Reason being is that is a working surface. So as your ring is going to walk up and down, the ring is going to like kind of press out every time you do. So as it presses out, you got your gap coming through there, and we were trained to have it at almost like a Mercedes logo. It's like here, there, and there. So you have your areas just there, but slightly to the right. So you don't have that constant ring gap eating away at that surface with the expansion, which probably some guys say it's better that way because you want the ring to set out and seal better. Personally, I just think that's going to wear out my engine. I've never done it that way over all the 20 odd years I've been working on engines. So yeah, we're not going to be doing it that way. But anyway, when in doubt, RFM is always a good choice to go to. So yeah, so anyway, what I want to show you, top ring gap, we're going to be looking at high boost applications, 0.008 of an inch. So you take your bore in inches times by 0.008 and you get your reading. So same there, same there, same there. And then we're going to work with that. So we know our bore is 86.5. And talking about that, we're going to know what our ring gap is. So this is the ring set, right? Fuel top ring there. Here we go. And then this is our coated skirt with the bore. So same thing with the bore. If you wanted to bore this, we want to go 86.5. We need to have that tolerances on there. So we're going to have 86.5 times 0.035. Can't remember what the math was, but we're going to check that now. So we're going to get our micrometer set. So let me get that set up quickly. Okay, so just for demonstration purposes, we're going to use the surface here. Don't work on top of your engine. Use a desk. This is just for educational purposes to show you guys in a more convenient way without the camera fluctuating all over the place how we're going to assemble this. So we're going to get our micrometer set out. We're going to get our telescopic gauges out. Let me get that set up here. I'm going to go with this guy, which is 92. So that's a little bit too big. We're going to go with these ones because we want to check 86.5. I have a little telescopic gauge here. Quite fun little things to play with. And put that in a safe location so we don't knock it over, damage our reading applications, and then we're going to measure our bore. So how these things basically work, I think I did the whole thing on that. So we tension over here, pressure gets applied there. It's a little bit clunky today. Anyway, so how we're going to do this, we're basically just going to pull her in just underneath the bore, tightly nip it, slow her down on the bore, and we're going to release it, and then nip it again, and what we're going to do at this same angle that we're in, pull right across there. That is our dimension. Hold it in tight, go to our little micrometer here. So let me set that up. Micrometer has been properly set to 0, and we're going to take it out to our dimension here. Gotta be really careful I don't scratch my surface here. I'm gonna do it that way. So I know it's gonna be like around about 86 something. So we're gonna take it out. So obviously this was done by an engineer, so they've got a lot better equipment than this than I have. Just for demonstration purposes, so you guys can see how it's done. I still don't have any good method to rebore a cylinder at home, but that's basically what we're gonna look at. And we're just gonna tighten that in. That was really shitty assembly. Yeah, that's a bit better. And we're gonna lock it there. Take this one out there, and our reading there is 86.46. So that is the solenoid. So we're not running, I think we're supposed to be over. So that's 85. We're on that line, so that's basically 86.46. Yeah, a little bit close, but a little bit small actually, but yeah, we'll just check that again. So now we're going to go back to this side here. Probably just has inaccuracy in my measurement method, so we did it that way. Now going to do the other way, bring it in a little bit on the way, nip that in, obviously with the thicker side to that. Small side is where you're pulling that up. We're going to pull it through, so we have it there, get it a fair bit down, and then you're just going to pull that through gently, nip it in place, check it again on the micrometer. You can hit the button. That's a bit of a better view. Let's see where we're standing now. So we're going to unlock that, move it back, put it back in. My hands are really shaky today. And it is exactly the same dimension as we had before. So that 0.45 discrepancy I have is probably just my lack of measuring skills. I'll just measure that again. So we want to get an average of 3 times. Yep, exactly the same. 86.46. This is the same reading. I don't know what I said before, but that's what I read now. So yeah, clearly I have a 0.6 discrepancy in my measurements. Pretty sure the engineers did a little bit better than I can, which is probably why it's better. But long story short is our axles are the same. So let me set that up. I hope you guys aren't too much distracted by the airplane in the background. It's been hard to get these videos done because just every day there's just something that needs attention. But yeah, so basically what do we do here? So we're checking our bore dimension like that and like that. And obviously it's a new bore, it's just been honed, so it's going to be correct to spec. Be careful if you guys want to do it like this, because you're measuring your piston's going to wear along, because your piston rocks around that axis, so it's going to be wearing those surfaces. And then I think there's one more thing we've got to do, which is basically our piston ring file. So we had that little calculation we had with the gap, so we are gonna quickly show you the piston ring file. So this is our ring file that we're gonna use. You have little dots there, ring goes on there, and you'll ground it. Now it says direction of rotation in this way. I disagree with that again, because where's the ring that I had now? Let me get that quickly and I'll show you guys a demonstration of why. Okay, so trying on the overhead camera here, hopefully I don't drop the camera. So with the disc rotating in this direction, it does work if it goes on that end. However, you have no control over the angle here, so you want to keep it in this area here, but that's this side of the axis. So if you do that, what's going to happen is the piston ring is going to lift up, especially if you do it over here. See, it's over there. So if you run it in this direction, this is actually going to unscrew. So it just does not make sense. Where if you were to go the other way, this is your direction of the application, your piston ring is not going to be lifted up. So let's see if I can get a better angle on that to show you guys a bit more. Let's just have a look at that center. So as you would basically hold this in this position, gently working on, this is a 220 grit, so it's going to take it down quite a bit. You can actually see it basically, just hold this here properly. You can see it basically lifts the ring. See how it lifts that ring? That's why you want to go the other way. See how stable the ring is there now? See if I can zoom in a little bit more. Okay, right, so if I do that, sorry for the shaky camera, and I hold it here in this position. Now watch what happens with the tip of the ring if I go in the direction of grinding. See how it's moving up? And if you go the other way, it stays nice and... this is the old ring, just to clarify, it's not the new ring. But basically you would have that grinding mix. And you don't want to like push it again, just gently. I'm basically applying just a few finger pressures. I don't know what a finger pressure is, but basically that, just gently working it down. And if you were to look at the other way, if you do it that way, you'll be able to see there that it actually has an uplifted end. See how it's not square anymore? If you compare the two to the side, look how that edge is almost like shiny at the top, and that one's like nice and square. See that shiny little corner there? That little stuff is going to affect your build. It's not going to run the way it's supposed to. So yeah, we're going to be doing the piston rings the other way. Okay, then just here for demonstration purposes on cylinder number 4, we're going to take one of our kits. So let's put this away here and grab our new pistons ring set. I have one already open, which I placed. Let me just allocate that quickly. Okay, so we have our nice new set of manly rings over here. There's the part number if you ever want to get some manly rings there. And then we have our ring set. So here we have our, that's the bottom ring, that's the top ring. Those are our oil rings. So I'm not really too worried much about the oil rings. They're not really that hectic, but the compression rings definitely are. I will definitely be looking into these because I have had one of my older centers did have an oil ring come loose. But these are least of a concern than the other ones. So I'm just going to put that back in the packet there, make sure they don't get oxidized or anything. Yeah, so 2 different ring types. Normally your second ring is a bit bigger. If we were to compare them, see your top second ring is a bit bigger and the other one's a bit smaller, and you have your indications of which has normally the little dot is what indicates the top side of the ring, but you do want to do RFM on that. Read the freaking manual basically if you guys don't know what RFM means, and make sure that you have your correct gap. So we're just going to use our top compression ring gap at this stage, and we're just going to stick her in there in our bore again while we haven't assembled the pistons yet, and then just use our nice little manly set over here, get it down just a little bit, and that is the most accurate way, I guess, to get them down to. You want to get it just down to the side to there so it's flush. You don't want to put it on too deep, but you also want to leave it at the top. So we're going to get our feeler gauge and then quickly going to check what that dimension is. Okay, so we have our feeler gauge here. I've just moved the gap a little bit there so you guys can see what I'm doing. And we're just going to take this ring gap, slip it in there, and it just fitted. It's not fitting. Oh, there we go. Fits nicely in there, and that's going to have like a nice firm feeling. It's not tight. You're not forcing it in. The ring kind of moved there a little bit. Let me just readjust that. Yeah, okay, that's nice and smooth. So you want to be able to slide it up and down. It mustn't be like stuck in there. So just be able to like slide it like that. That's 0. Those are inches. Those are millimeters. And let's just go one size up. This is just like a low-tech feeler gauge that I'm using here. And let's see, so we want to go one size bigger. Let me just get that quickly. Okay, so I've got 3 sizes here. Focus, thank you. So this is 9 thousandths of an inch. That goes in as well. Relatively smooth, so you can just see the difference there. That has not moved again, so we just want to get that a bit in. I don't really like sliding the ring up and down the board for no reason. And then this one here is the 0.1, 2.78, and then we're just gonna slide that in there. And you see it doesn't go. It doesn't slip in there at all. It just doesn't want to go. So we know this is too big. This is where the ballpark we're at, hundredths of an inch, yeah, hundredths of an inch, and then thousandths of an inch there. So we're gonna have to grind this one down. So let's do the calculation what we need. Okay, right, so we got a calculator here. So 86.5 millimeters is 3.455 and that. So we're gonna multiply that by 0. What was it dimension again? Let me just check that. Measure twice, cut once. Put the paper over here. All right, so we have our gauge there. Second ring, 0.008 inch, so 0.008 inches. That gives us a dimension of 0.027 inches. Right, so that is going to be our ring gap. Now, if you remember correctly, we were at 0.1. So we're basically going to minus 0.01. And that means we have to take off 0.17. So we're just going to add that again. 0.01 and we'll take it again. So obviously do check your calculation again. So that's 86.5 is 3.4055 multiplied by 0.008. Obviously if you're going to running lower boost, that's going to be a lot smaller number. Check that again, that is 0.027 inches. That's for your thermal expansion. So let's grab this piston ring over here. So as the engine heats up, your metal's going to expand, and it's going to come closer and further away. So we want to make sure that that gap there is going to be good. So if we were to grab our little feeler gauge here again, go down to 2.27 inches. So 1, 10, 25, 28. Do I not have a 27? Oh, that's a bit unfortunate. So 2 is going to be too big, so we don't have that. So we can pair a, let's see here, if we can get 27 in another way. So if we had 15 and 12, we can do it that way. That's 14, 13, 12. There we go. So we can add our 0.15 feeler gauge. 0.15 feeler gauge with our 0.12, add those together, you get 27, and then that's going to have to be the thickness of our ring gap. And as you can see, currently she ain't gonna fit, not at all. And this is the port where you want to work it down and measure it a bit. So we're going to work this one down quickly to this dimension. Let me get that set up for you guys. Okay, this video is getting a little bit long, so I don't want to waste too much time on this here. So what we're going to do with this, we're first going to work down a little bit on the one side and then the other side using these two pins as our positioning. We're going to work it down there, because like I said, we're about half of what we need to be in terms of thermal expansion. So we're going to work this down a little bit. Be careful when you do this, because once you do it down it too far, she's gone. You got to get a new set. Well, I don't think you have to get a whole new set, but that's what the manufacturer recommends on that. So we're going to work this down a little bit, gently working it in, holding it in place, working it down slowly. This will be better if it was stuck to the bench. So we're going to hold that there, keeping in mind that you want to keep the pins against that one at all times, keeping it nice, flush and level. I'm actually being stupid, I've got to do it this way. Yeah, there we go. So again, with that rotation, look how much easier that is compared to the other direction. Just gently going to work it down. Other side, gently work it down, gently work it down. And then we're going to stop there, and we're going to have check again. Again, we're here at the ones, so we're going to slip this in. Today is getting a bit long, so I think I might have to cut off this one here because I've got a lot of things to do. It's about 8 rings. Drop that down there. Correct length. Get our feeler gauge. Set up to the correct dimensions. Double check. Measure twice, cut once. And check our ring gap on there. And she's still not there. So we can actually now take our other blades and say, well, that's 22. So let's maybe check a 20. And then work on there. So okay, well, if we get to 20, we're going to be close. So we're going to work on there. 20 is not there yet, and then we're going to work it down to say I think it was 15. I think it was. Yeah, there's a 15. And we're going to work it in there again and see. Okay, well, 15 still is good, and you'll kind of get the feel of like how far you still have to go. As you can see, we haven't really gone very far because I don't want to overgrind these things, because it took me bloody 3 months to get them, so I don't want to work on that again. Yeah, right guys, so I'm going to call it there. The video's getting long. There are some more things we probably want to do with the pistons, but that covers your basic. We covered the metallurgy of the pistons. Let's get a better view here. Alright guys, so I'm pretty much going to finish it up there. That's everything you need to know. We will be doing our rods next, and also I'll cover everything in depth on what we need to do with these ones. So these are going to be our next rods. We're going to be comparing them to old ones, look at metallurgy. We're going to cover the inertials on these things, and H-beam versus I-beam and all those other things. Yeah, so guys, thanks for following along for our demonstration purpose. Really appreciate you guys for watching the videos. Like I say, this is for the community, so the more you guys watch it and tell people about it, the better the word's going to spread for things. So probably not the best t-shirt in the world, but when you guys get the gist of it, there's a lot of information here that you guys can work on and help you to find your purpose and everything. So in the future, Oh, I can even see the future work marks there. So yeah, in the future we're probably going to do a lot more things. Obviously I do need to get this car done, and filming things does take quite a bit of time, so we're probably going to be speeding things along. But yeah, so that covers everything of our pistons, our 2618 high revving pistons versus low revving pistons. You can even see some machining marks there. So even though they're exactly the same, they're not made equal. And also just look at, they haven't even touched on that, but basically your valve clearances here is obviously more important. So these are normally run with people with cams, bigger valves and things, so you need that little more spacing that you need. And yes, we've covered the weight, we've covered the balancing, we've covered the metallurgy, we've covered, I haven't covered the skirt sizes here, but obviously it's for different applications. So with your exhaust side being, which side? Exhaust that side, yeah. So if the exhaust size being that side, and your intake side being here, you obviously have a cooler side, you have less weight. So that's probably, you can see the cross-sectional area, the difference in shape there, where this is a more triangular shape, where this is a more square, strong. You can see your cross-section here is a lot bigger, thicker, it's a lot wider there, your gudging pins are bigger. So at least that gives you guys an idea of what to look for in terms of quality, in terms of pistons. I really hope this helps anyone with the engine bolts and projects that you're working on. Yeah, so really appreciate it, guys. We will be getting more into the next one. I got to get to work on this because it's going to take me a whole day to get through these pistons, and I'll probably do the rods maybe tomorrow sometime. We'll see how it goes. Thanks guys for watching, and I'll see you on the next one. Cheers.